Hello everyone. For those of you who don't know me, my name's Mr. Harris, and I'm going to be helping out your class for the next few weeks while Miss Warrior's away and Miss Gum has you guys. So I'm going to be producing some videos or coming in to the classroom to help you out. I'm unfortunately in COVID isolation at the moment. I do have COVID, so I'm not going to be at school for the next week, but come week 2, I'll be making visits into your class and taking you through some of this content. But for the next week, there'll be this video is probably going to cover most of this week, or if I need to do another one, I'll do another one later on, taking you through the beginning of some of the ideas. So if you did have any questions, obviously Miss Gum's there to help you out, but you can also send me an email or a direct message this week if you need something. Otherwise, next week I'll be coming into your classrooms and you can certainly talk to me then. All right, so let's get started. We're starting a new topic on chemistry, chemical reactions. A little bit later in the topic, there'll be some choice for you guys around how you want to move forward with it. But to start with, we're going to get some basic theory done. And then your choice will be around how we apply that later on in the term. So let's start with a chemical reaction. So here we go. Computer, catch up with me. There we go. All right, so for the most part, atoms don't exist on their own. So if you were to go and look at stuff that's out there in the universe, most of what we would find around us is not actually single atoms. They generally react to form molecules or lattices, the two types of structures that they create. So the only ones that really don't do that, certainly don't do it on Earth or anything like that, is the noble gases. They're the ones that are in group 8, the final column of the periodic table. So if you look in sector, there is a periodic table attached into today's lesson, or the first lesson of the term. So the very final column on the right, they are all the noble gases, and they don't react with other things. So all of the other atoms don't have a full outer shell. They don't have 8 electrons in their outer shell. And so because of that, that's actually why they react. So they attach onto other atoms so they can get a full shell of electrons. Those, excuse me, those atoms in group 8, the noble gases, they actually already have a full shell of 8 electrons. So they don't need to do any more reactions to be full. So when we have just one thing on its own, it's called an atom. When they stick together, we can get molecules, which look kind of like this. This is a pretty common one that you'd be familiar with. This is water. So we have 1 oxygen atom and 2 hydrogen atoms there. Or we can get things called crystal lattices. This is an example. This is sand, silicon dioxide, which you can see is a large, complicated structure of lots of pieces joined together. So atoms stick together, they form these molecules or they form these lattices, and sometimes they do it with just atoms that are the same as them. So oxygens with oxygens or hydrogens with hydrogens, or sometimes they combine with different types of atoms. So if it's only one kind, we call it an element. If it's more than one kind, it is called a compound. So these are just 2 little ways we can sort of represent that. You can see on the left there, the elements, they're the same. So 2 of the same type of particle. The compounds, obviously, we've got the different types in there as well. Now, some of the compounds can be really complex, lots of different types, or they can be just 2 types like you see in this diagram. So molecules, once again, 2 or more atoms joined together. Some molecules are elements. You can see a few different ones here, oxygen, phosphorus. Some molecules are compounds. A couple of different examples there for you to look at. And then we also have mixtures. So a mixture is where we have some elements or compounds combined together but not actually bonded, so not actually attached to each other. So this would be an example of a mixture. Here we've got a couple of different molecules and then a single atom on its own there. So that would be one of the noble gases. And you can see that the elements, the element molecules, the two of the same that are bonded together, and then the compound molecules, they're not actually attached to each other. So we would classify that as a mixture. So most of the things we see around us are compounds of some form or another. And what's important to know about compounds is that the properties that they display, so what they're like, are completely unrelated often to what makes them up. So there's just over 100 different elements. Only about 90 of those actually occur naturally. And of those 90, there's only about 20-ish that are common at all. Most of the other ones are really, really rare, unusual to find. So from realistically about 24 ingredients, they can combine for the billions of different things that we see around us. And this all happens by chemical reactions. So a chemical reaction needs to take place to make something new. So there's a picture of a couple of coloured liquids being mixed, because that's what everybody thinks of when we think of a chemical reaction. Not always the case, though. So almost everything has been made by some chemical reaction or another. And what a chemical reaction actually is whenever atoms are combined or rearranged to form something new. So I'll just say that again. They're combined or rearranged and they form something new. So these new substances are often very different to what originally made them up. So a really common example of gases that we have around us in the air, oxygen and hydrogen. Now you may not know this, but hydrogen is actually really explosive. If you just get a pure hydrogen, highly explosive stuff. Oxygen is obviously pretty important for us. We need it to live. Now, if we react those two things together, hydrogen and oxygen, what we end up with is H2O. Now, H2O, you know, is water. Now, water is obviously not explosive, and it's also not something that you'd actually want to have in your lungs, is it? So hydrogen and oxygen, very, very different properties as gases to water, a liquid that is the product of that reaction. So it's definitely a different process than just mixing things together. You get something very, very different at the end of it. So there's lots of things that we see changing that are not actually new substances. So like the classic example, which I'm sure you've seen a number of times now, is freezing water. So you freeze water, it becomes a solid. It looks so different to what it did to start with, but it's still made of exactly the same materials. It's still H2O. It's not actually any different. This is not a chemical reaction, it's a physical change. So not a new substance being produced, just a different way of that thing acting. So it's just acting in a different way. So chemical and physical changes are things that we can see around us. So physical changes, there's not a new substance being formed. Some of the properties may change, but the substance actually stays the same. So size, shape, state are all examples of physical changes. Something breaks or melts or freezes, etc. Quite often these are pretty easily reversed. It's not always the case, certainly, but it's often more easy to reverse a physical change than a chemical one. So a chemical change, we're getting a new substance. So the particles have been moved around and recombined to create something new. So these chemical reactions are what form these chemical changes. So sand, gravel, and cement get mixed and we end up with concrete. If you add Alka-Seltzer, like an aspirin tablet, into water, some of the chemicals dissolve and then they react, producing gas. In general, chemical changes are much more difficult to reverse and often they are irreversible. Not always 100% obvious whether things are reversible or not. So things that we actually want to do to identify whether or not a chemical change has taken place. or a chemical reaction has taken place. There's a few key criteria that we use to define what these changes are, or say that yes, if this is taking place, it's probably a chemical change. So, first one, the production of gas. If there seems to be a change in mass, or there's the production or absorption of energy. So have a look at a couple of these examples very briefly. So when you're cooking a cake, you might get some gas produced, or we talked about the aspirin in water example. You can have a read through some of these in a bit more detail. The PowerPoint is in sector. So often the mass of something seems to change. So if we do a chemical reaction, something may be given off, or it might actually react with something in the air and get heavier or lighter than it seemed to be to start with. Come back to that idea a bit later when we look at the law of conservation of mass, but that can be a sign that a chemical reaction has taken place. And if you get energy produced or being absorbed, so things light up, they get hot or they get cold, this is often an example of a chemical reaction. There's a few more things that we look for: a permanent color change, or the formation of a precipitate. So if a chemical reaction has taken place, then a color change may take place. So if the change is permanent, not something that starts glowing because it's getting hot and then goes back to normal, but stays the different color, then that might be sign of a color change. Or a precipitate is another example, which we'll get an opportunity to do some practicals around later. A precipitate is a solid that forms when you mix two liquids. So you just pour two liquids together and a solid actually comes out. So something that you can actually do in your own home, if you were to add orange or lemon juice into milk, it will curdle and create a solid out of that milk. Something that we would do in the lab, lead nitrate and potassium iodide will turn yellow, and a yellow powder will actually drop out. So a solid there. So here are a few examples. What I'd like you to do now is have a look at each of these. Pause the video, have your best guess at what you think the answers are, and then I will come back and run you through those solutions in just a moment. All right, so pause the video now, and we'll go with that. Okay, so hopefully you had a chance to give these a go. So if we adding salt to water, we can see that it looks definitely different. The salt disappears, but that is actually a physical change because once you get the water out, so if you were to evaporate the water out, you get salt back in the container, exactly the same material as what you had to start with. If we are to burn a candle, let's think about the signs that we might see. Is there a gas given off? Yes, you get smoke there. Would there be a change in mass? Well, we can see over time the candle gets quite a lot smaller. You'd expect that to actually change how heavy it is, so definitely that. Is there energy being produced? Well, yes, you see light, you see you get heat off there as well. And the final one is a permanent color change. So obviously a candle will turn black, or anything burning will turn black progressively as it burns. So that is definitely a chemical change. So I'll go through the rest of these a little bit quicker. So frying an egg, that is a chemical change. You can't unfry it, you can't reverse it by putting it back in the fridge. Making an ice block, that is physical though, because it happens when it gets cold, and then when it gets warm again, it melts once again, so reverses that process. So burning gas, that is chemical. Making concrete is chemical, as we already saw. Adding water to a cup of soup, now we've classified that as physical. You could make an argument that is a chemical change, a bit like concrete. So physical is probably the best answer there, but if you said chemical, we'd probably accept that. Burning a sparkler is chemical, and if something is rotting, it's not something we can reverse. That makes it a chemical change as well.